my name is Matthew Nunes, and I'll be talking about instrumenting compilers to deobfuscate malware. So the agenda for this talk is that I'll start by providing a basic introduction to compilers and how they function, and then go on to the main content of this talk, which is using the compiler known as Babel to deobfuscate JavaScript. So a bit about me to begin with. So some of you may have noticed the picture on the title slide was of the capital of Wales, which is Cardiff, and that is where I'm based. I am immensely privileged to be working for PwC's Global Threat Intelligence team as a reverse engineer. And if you haven't met the incredible people in this team, I'd love to introduce you. So currently, my main focus is on crime and financially motivated threat actors. But before this role, I worked as a vulnerability researcher / exploit dev. Prior to that, I worked in software dev. Prior to that, I was a child. So, before covering the main content of this talk, we need to cover some basics about compilers. Now, if there are any compiler devs in the audience, I do apologize for some massive oversimplifications. So, we can roughly break down what a compiler does into 3 stages for the purposes of this talk. And the stages are parsing, transformation, and code generation. Parsing takes the source code and converts it into a more abstract representation. And it can actually roughly be broken down into 2 stages, lexical analysis and syntactic analysis. In lexical analysis, the code is transformed into tokens that are essentially an array of objects representing the code. In syntactic analysis, these tokens are then transformed into an abstract representation that shows the relations between them, and this is referred to as an abstract syntax tree, or AST for short. In transformation, the compiler walks down the abstract syntax tree to transform the tokens, or now nodes, into a new language or a different form of the same language, as we'll see later. And this is actually the phase that most of this talk is going to be about. Finally, in code generation, the tree is then written out into new code, or basically stringified. So let's see this as an example. So we're going to look under the hood of a compiler that doesn't change code from one language to another, but just replaces every addition symbol in your code with multiplication. And as an example, assume that the program we're compiling is a single line of code, that is the line 2 plus 3. So in the first stage, the code is transformed into an array of tokens, as seen on the slide between the curly braces. So we have the plus symbol, which is of type operation. We have the values 2 and 3, which are literals. The next stage is to transform this into an abstract syntax tree. So this is the abstract syntax tree, and it shows the parent-child relationship between each of the tokens. And as you can see, they've been embellished with a bit more information. So we have a program which is composed of an expression statement, which is formed of a binary expression. And notice it's got the property operator, and the value of that is the plus symbol. It then has 2 children, which are the literals, with values 2 and 3. So the next thing we need to do is actually transform that to replace the plus symbol. And we're going to assume that there's an inbuilt traverse function that takes 2 arguments, the tree you want it to walk, and an object containing the transformation functions you want it to apply. So in this case, this is the method to change plus symbols to multiplication. Now, transformation functions are often referred to as visitors or visitor functions, and they're actually called that because as the tree is traversed, if the node type that function is looking for is encountered, the function is called, and the relevant node is passed as an argument. So in this case, we're looking for a binary expression. The function within this object, imagine it's similar to an event listener, as the function will be called when the node of type binary expression is encountered. Now you'll notice by default, the first argument passed through a function is not just the matching node, but the path to it, as it allows you to refer to the node's parent as well, if you need to. Now, all this function does is, when it encounters a binary expression with a plus symbol, it changes it to multiplication. To refer to the node pointed to by the path, we access it using .node, and then access any relevant properties of the node using dot and the property name. So in this case, operator. So as the tree on the right is traversed, when it encounters the node we're looking for, it calls our visitor function, which changes the node. And visitor functions is actually what we're going to focus on for our deobfuscation. Finally, as I imagine we all expected, during code generation, the abstract syntax tree is recursively traversed and written out into code. In this case, the plus symbol has been replaced with multiplication. Now, just to say that a lot of my knowledge around this comes from an educational compiler known as the Super Tiny compiler, and I would highly recommend you check it out. So that's compilers. And now that you're all expert compiler developers, let's talk more specifically about the compiler I used, Babel. So Babel is a JavaScript to JavaScript compiler, otherwise known as a transpiler. And it was originally conceived by its creator as he was quite excited about all the new features that ECMA Script 6 offered. Now, for those that don't know, ECMA Script 6 is the 6th version of the JavaScript standard that released a bunch of new features back in 2015. The problem was that not all browsers supported it when it first came out. So rather than wait for them to add support, Babel was created to transform ES6 code into older, backwards compatible JavaScript, allowing its authors to start using the features immediately. Personally, so I've never been that excited by the release of a new standard, but that's just me. Now, obviously, it can also be used to deobfuscate JavaScript. And one of the main blogs that I learned a lot from was by Steak Enthusiast, not the real name, and I would definitely recommend checking that out. So, on to the main content of this talk. How do we use Babel to deobfuscate JavaScript? So a bit of context on the file we'll be analyzing. So we first encountered it during an incident response, and the campaign seemed to be targeting users in Germany, which is ideal if you're looking for ideas for a conference talk in Germany, but admittedly less than ideal probably on every other front. Now, the way the infection worked is that the victim received an email with an SVG attachment, which, when opened in a browser, downloaded a script that essentially displayed a download button, and if that button was clicked, a zip was downloaded, which contained the obfuscated JavaScript that we see. Now, we didn't observe the final payload, but when we cross-checked our IOCs with other open source reports, it was quite evident that the next payload would almost certainly have been StrelaStealer. And the picture on the left is on my right, is of the obfuscated and unbeautified JavaScript. And yeah, as you can see, it is not beautiful. So I'll just provide a quick introduction to StrelaStealer itself prior to continuing with the main content of this talk. So it was actually first reported on in November of 2022 by DCSO SciTech. And it's an info stealer, but unlike your average info stealer, it targets only two applications, Outlook and Thunderbird. And for both of them, it's trying to capture login data. Another unique feature of StrelaStealer is that its phishing campaigns seem to primarily target users in a handful of countries, so namely Spain, Italy, Germany, and Ukraine. And the actual stealer binary that is distributed is typically a DLL. And interestingly, actually not a lot has changed in its stealer functionality between 2022 and now. So that's StrelaStealer, but let's get back to analyzing the JavaScript loader. So the first thing we do for any JavaScript malware is we beautify the code, as that will just make it look a little bit nicer. And the other thing is my manager frequently reminds me that reverse engineers are just glorified pattern matching algorithms, so we need to constantly be on the lookout for patterns. The first pattern we see is that several variables are initialized over and over again. So the same variable is often repeatedly initialized. Now, obviously, only the last value that the variable is initialized to actually matters. So as you can see in the picture, ich is initialized to R, to B, to I. V, obviously, I realize in German, ich means I, but they immediately overwrite that with V, just adding insult to injury. But sadly, we only care about what it's assigned to last, which is the letter V, as that overwrites all the previous assignments. The second thing to note is that the last two lines contain the actual functionality using the variables. And we see that those letters are concatenated to produce commands. But before we get to that, let's clean up the variables. So, when using Babel to transform your code, the first thing you should do is put it in astexplorer.net. That is an open source project that takes your code and prints out the abstract syntax tree on the right. Now, on the left, we have one line of code from the malicious sample, the variable ilco being assigned the letter F. On the right is a small portion of the subsequent tree. The things to notice is the assignment expression, which has the operator, which has the property operator whose value is the equals sign. That expression then has a left and a right property. If we expand those, in the left property, we have a node whose type is identifier. That is the name ilco, which is with the variable name. On the right, we have a node whose type is string literal with the value f, and that is the variable value. So what do? Well, to begin with, there are some common setup operations that we need to perform. And as you'll see later, the first thing we'll probably need to do is read from the file system, so we need the fs package, obviously. But then there are also several Babel packages we need. So the types package lets us check the types of the nodes in the abstract syntax tree, amongst other things. The parser takes our malicious code and produces an abstract syntax tree. The traverse function takes our abstract syntax tree and a visitor function and modifies it accordingly. And finally, generate takes our modified abstract syntax tree and produces raw code output. That's all our imports. We read the source code file after that. We parse it to generate our abstract syntax tree. And in this case, we're also going to create a global variable that is essentially a hash map or a dictionary to store a mapping from variables to value. So let's actually traverse the tree. Now, we need to traverse the abstract syntax tree matching on assignment expressions. Every time we encounter one, we'll store the variable name and the value in our map. And though it'll encounter the same variable multiple times, it'll just keep overwriting it. It'll keep overwriting the value with the new one, and eventually the map will contain the mappings of variable name to its last assigned value. So that's the first stage, and that won't actually change the code. It's just going to populate our map, which will be useful in a minute. So we now traverse the tree again. Again, we match on assignment expression and store the variable name and value. But this time, when we encounter a variable assignment, if it doesn't have the same value as the one stored in our hash map, we delete it using path.remove, since it's not going to be used later. When we look at the code now, each variable is assigned once, and instead of thousands of lines of code, we have 64. So the next thing for us to do is to work on those last 2 lines and see if we can replace the variables with their actual values. So if we take a small portion of line 63, the way it's represented in AST format is by a left-heavy tree of nested binary expressions. Each binary expression represents a plus symbol, and then the variable itself is stored on the right in reverse order. So we have RHP, FYIA, IC, and that's because the tree is traversed in a depth-first manner. So yeah, as I said, RHP is the first identifier, then FYIA. You'll notice I've stopped trying to pronounce the variable names. That is intentional. Now, just to say, this obviously isn't the whole tree, it's all I could fit. So that image looks like this in text form. So based on the representation on the right, what we're looking for is identifiers, as they represent the variable stored on the right. And we want to replace them by string literals containing the values. But to ensure that we only edit the identifiers that we want to replace, we check that the parent is a binary expression using the types package we imported earlier from Babel. As I mentioned previously, it lets us verify the types of nodes in an AST. And as long as the conditions match, we perform the replacement. Now you'll notice that for the sake of brevity, from now on, I haven't listed the traverse function at the bottom, but know that it is called after each function. So now, when we look at it, we can see actual commands. We have eval and quit. And after eval, we have a long line of code that is represented as a string. So we need to extract that and beautify it. But before we do that, it would be nice to have eval as a continuous string without the plus symbols in between each letter. So how do we go about that? Well, I won't actually spend too long on this, but what we do is call Babel's inbuilt evaluate function on the binary expression. Basically, if the value can be determined at compile time, evaluate will do it. And not only does it return the value, but it returns whether it's confident in its return value. If it's not confident, we don't want to replace the value, and we want to log an informative error message. If it is confident and the value returned is a string, we again use the types package from Babel, but this time to create a string literal that we replace it with. Now notice that we've done path.replaceWith, not path.node.replaceWith. And that's because path knows we're referring to the node it's pointing to, and therefore it'll replace it safely whilst fixing the references, metadata, etc. So now we can see the characters have been concatenated into a single string, which just looks much nicer. Let's now extract the string that comes after the eval statement. So, as you can see on the right, we want a call expression, but in order to ensure we get the right one, we only want it if it has one argument, and that argument is a type of string literal. And if we do have that, we'll store that in a global variable that I defined outside this presentation called newScript. And then we'll take the output of newScript and extract the string from it, beautify it, and we get that. So what we have here is all the variables we defined earlier concatenated to create commands. So what do? Well, we do what we've done before. We replace all the variables by their values, as we've done previously, then combine the individual characters using evaluate into like a single string, and we get this. So finally, we have the C2, registry keys, file paths, amongst many other IOCs. Essentially, what this script does is it copies itself to the app data folder, it contacts its C2, and it sets up persistence using the registry so that it's run if the machine is rebooted. And then it just sits and waits in a loop for further data from its C2. So this here actually ends our summary of how you could go about using Babel to deobfuscate JavaScript. And using this technique, we were able to automate the extraction of the C2 address from just over 6,400 samples, which, as you can imagine, allows us to provide a much more complete picture to SOC analysts and incident responders. A major benefit of this technique is that, unlike with other techniques, it didn't fall apart when we encountered variations in the code. And we're still exploring the breadth of this technique, but we are finding we can use it on malware from other threat actors. So as we say in Wales, diolch yn fawr iawn am wrando. Thank you very much for listening.